The electrical grid delivers power at a fixed voltage and a fixed frequency, but the physical world rarely demands a constant, unwavering force. An electrical drive bridges that gap, forcing a motor's electromagnetic torque to perfectly match the mechanical load, whether cruising at steady state or violently accelerating. To do this, engineers first map the physics of the load. Mechanical demands generally fall into three distinct profiles: constant torque, variable torque, and constant power. Look at the flat horizontal line. That represents a constant torque load, like a heavy hoist. Whether creeping forward or at maximum velocity, the required rotational force remains exactly the same. Now look at the asymptotic curve. This is a constant power load. Here, the mechanical work stays the same. Torque and speed are inversely proportional. If the machine speeds up, torque must drop. A classic example is a paper mill winder. As the roll winds, its diameter increases. To keep tension on the fragile paper perfectly uniform, the motor slows down as the roll gets larger, maintaining the exact same mechanical power. Contrast that gradual tension with a steel blooming mill. This load is subjected to extreme transience. When a slab of glowing steel hits the rollers, the motor instantaneously delivers a massive spike in torque to push the metal. Then it physically breaks that momentum just as quickly to reverse the steel. We must take a rigid utility supply and manipulate the specific physics of DC or AC motors to satisfy these wildly different mechanical profiles. For over a century, the standard solution to this problem was the direct current, or DC motor. It dominated heavy industry because of its orthogonal, fully decoupled magnetic architecture. This is the governing equation for DC motor speed. Speed, N, is determined by the voltage supplied to the armature, minus the internal voltage drop, all divided by a constant times the field flux. For an engineer, this equation reveals exactly two levers to pull: armature voltage, V, and field flux, phi. Because the armature and the field windings are physically separate circuits, controlling them is mathematically simple. You can alter the armature current to dictate torque without interfering with the field flux. That separation presents a distinct challenge at startup. When a DC motor is at a dead stop, it generates no back electromotive force, or back EMF, to resist the incoming power. If you apply full voltage immediately, the inrush current will melt the armature. Getting the mass moving is only half the equation. You also have to stop it. One method is dynamic or rheostat braking. The controller disconnects the motor from the supply and reconnects it across a physical resistor grid. A much harsher method is plugging. Here, the controller suddenly reverses the supply voltage polarity while the motor is still spinning. This forces the motor to fight its own momentum, slamming the load to a halt. It requires incredibly robust hardware to survive the electrical stress. The most efficient method is regenerative braking. If the mechanical load drives the motor faster than its set speed, like a hoist lowering a heavy weight, the back EMF exceeds the supply voltage. The motor naturally becomes a generator, pushing power backward into the electrical supply. These heavy torque capabilities and regenerative braking profiles made DC series motors the undisputed choice for early heavy transit systems like subway networks. This chart shows the torque speed curves for a separately excited DC motor. To operate below base speed while maintaining constant torque, you throttle the voltage. Every time you reduce the armature voltage, the motor speed drops along a perfectly parallel line. To achieve that smooth voltage reduction, modern DC drives use a controlled rectifier, typically built from silicon-controlled rectifiers, or thyristors, arranged in a single-phase or three-phase bridge. By delaying the exact microsecond these thyristors fire, an interval known as the firing angle, alpha, the drive chops the incoming AC sine wave into fragments. This tightly controls the average DC voltage applied to the armature. The electronics to do this are incredibly straightforward, but the physical DC motor requires carbon brushes dragging against a copper commutator. That friction limits maximum speed, generates sparks, and requires constant maintenance. To scale up and operate in harsh environments, engineers had to abandon the simple math of DC and move to alternating current. The AC squirrel cage induction motor is a solid block of steel and copper. It has no brushes, no commutator, and is virtually indestructible, but it is mathematically rigid. It relies entirely on a rotating magnetic field in the stator to induce current in the rotor. Look at the synchronous speed equation. Speed equals 120 times the frequency, divided by the number of magnetic poles. To control the speed of an AC motor, you can only manipulate two variables, the poles or the frequency. Early attempts relied on pole amplitude modulation, physically switching the winding connections to change the number of poles. This only yielded discrete, clunky jumps in speed. For smooth, continuous control, frequency is the only viable target. You cannot simply lower the voltage like a light dimmer. In an induction motor, maximum torque is proportional to the square of the voltage. Drop the voltage by half, and your torque plummets to 1/4. The motor will stall. We must change the frequency. But altering frequency alone breaks the physics of the machine. If you drop the frequency while keeping the grid voltage high, the magnetic flux inside the motor saturates the iron core. The excess energy manifests as massive thermal losses, and the motor quickly burns itself out. This chart illustrates the solution, the volts per hertz ratio. To safely alter the speed of an induction motor without oversaturating the core or sacrificing torque, the drive must perfectly balance the applied voltage against the applied frequency. If frequency drops, voltage must drop by the exact same proportion. We achieve this using a voltage source inverter, or VSI. It operates in two stages. First, a diode rectifier takes the fixed grid AC and converts it into a stiff, stable pool of DC power, smoothed out by a massive capacitor bank known as the DC link. Next, the inverter stage takes that DC power and uses insulated gate bipolar transistors to chop it into pulses. By rapidly varying the width of these pulses, a technique called pulse width modulation, the drive artificially constructs a brand new AC sine wave with the exact voltage and frequency the motor needs. An alternative architecture is the current source inverter. Instead of a capacitor maintaining a stiff voltage, the CSI uses a massive series inductor to maintain a stiff, constant current. Because the current is strictly controlled, a CSI drive is incredibly fault-tolerant. It can also naturally reverse voltage polarity to feed braking power back into the grid. However, that large inductor makes the physical footprint of the drive massive. Today, engineers often use a hybrid approach, the current-regulated voltage source inverter. This uses standard compact VSI hardware, but implements advanced software control loops to force the drive to output the dynamic, precise current profiles of a CSI. To get precise control out of a rigid AC motor, we have to isolate it from the power grid entirely. We tear the raw, rigid utility power down to direct current and completely rebuild it from scratch to fit the load. There is a completely different approach to AC control. If we look back at our speed equation, assuming our frequency and poles are locked by the grid, we have one variable left, S, the slip. Slip is the difference between the speed of the rotating magnetic field and the physical rotor. In a solid squirrel cage motor, slip is dictated entirely by the load. To manipulate it, you need a specialized machine called a wound rotor induction motor, which routes the rotor circuitry outside the casing via physical slip rings. The simplest way to control slip is rotor resistance control. By wiring physical resistor banks into those slip rings, you can alter the motor's torque curve, providing high starting torque while limiting the massive inrush current. As a primary method for speed control, it has a fatal flaw. You are quite literally burning energy to slow the motor down. The extra power pulled from the stator, known as slip power, is dissipated into the resistors as raw heat, destroying the drive's efficiency at low speeds. This diagram illustrates the power flow in a wound rotor motor. Air gap power enters the rotor and immediately splits into two streams, the mechanical power turning the shaft and the slip power. Instead of burning that slip power in a resistor, we can intercept it and recycle it. This is called slip power recovery. One method is the static Kramer drive. Here, the slip power is pulled from the rings, rectified into DC through a diode bridge, and fed into a separate DC motor that is mechanically coupled to the exact same drive shaft. The Kramer drive takes the electrical energy that would have been wasted as heat and uses it to mechanically assist the main motor, directly supplementing the output torque. Alternatively, we have the static Scherbius drive. Instead of a secondary motor, the rectified slip power is routed through a line-commutated inverter, converting it back into AC and pumping it directly back into the facility's power grid. These architectures are highly specialized. They are incredibly cost-effective for multi-megawatt variable torque loads, like massive municipal water pumps, that only need to operate just a few percentage points below their maximum synchronous speed. By treating slip not as an inevitable mathematical loss, but as an interceptible energy stream, rotor side control transforms standard induction motors into highly efficient heavy industry workhorses. The evolution of electric drives forces engineers into a strict dichotomy. You can choose the simple, linear electronics of a DC drive, or the incredibly complex power architectures required to control an AC motor. This matrix outlines the trade-off. DC drives offer low electronic complexity, but high mechanical wear. AC variable frequency drives require massive electronic complexity, but zero mechanical wear. And slip recovery systems sit in the middle, offering high efficiency but restricted speed ranges. For decades, the complexity of AC control made it prohibitively expensive. But the plummeting cost of microprocessors and high-power insulated gate bipolar transistors has made the AC volts per hertz drive the undisputed universal standard for nearly all new installations. In massive industrial complexes, centralized control rooms monitor and orchestrate thousands of these disparate drive topologies. Rectifiers, voltage source inverters, and Scherbius drives are all networked together to perfectly optimize facility-wide energy consumption. There is no single perfect drive topology. An engineer's primary job is to map the physical limitations of the motor against the extreme thermal and transient demands of the mechanical load. Over a century, we have systematically eliminated mechanical wear and physical limitations, not by changing the fundamental laws of physics, but by mastering the complexities of solid-state power electronics.
Thanks for watching. Please visit the channel for more content. Don't forget to subscribe, like if helpful, and comment if something is wrong.